Black holes have become the celebrities of our cosmos. They are on the covers of science magazines. They are in our movies and our television shows. They have captured our imagination like almost nothing else. And for good reason. A point in space where gravity is so strong that nothing, not even light itself, can ever escape. That is an astonishing idea. That is the kind of idea that makes you pause and stare at the ceiling for a while. But here is the thing. Black holes are just the tip of the iceberg. They are just the appetizer. They are the introduction to a much stranger menu of objects that the universe might be hiding from us. And tonight, we are going to explore that menu together. Before we drift further into the unknown, I would love it if you gave this video a like and subscribe to Cosmic Drift. It helps our sleepy little community grow closer to the stars. Now, let us think about something for a moment. Think about the history of black holes. Not the history of the objects themselves, but the history of our knowledge of them. Because that history tells us something very important. It tells us that the universe has a habit of proving our mathematics right, sometimes centuries after we first wrote down the equations. In 1783, a man named John Michell was sitting in his study in England. He was a geologist, a clergyman, and what we might call a natural philosopher. He had a curious mind, and one day that curious mind led him to a strange thought experiment. What if, he wondered, there was a star so massive and so dense that even light could not escape from it? He called these hypothetical objects dark stars, and then the world mostly forgot about his idea for over a century. Jump forward to 1916. The world is at war. In the trenches of the Eastern Front, a German physicist named Karl Schwarzschild is serving his country. But even in the chaos and horror of battle, his mind is working on something else. He is working on Einstein's new theory of general relativity, which had only been published the year before. And Schwarzschild finds something astonishing. He finds an exact mathematical solution to Einstein's equations, a solution that describes what would happen if all the mass of an object were concentrated into a single point. That solution predicted black holes. It predicted the event horizon, the point of no return. It predicted that space and time would twist and warp in ways that seemed impossible. Schwarzschild sent his calculations to Einstein, and then, tragically, died of disease on the front lines. He never knew how important his work would become. But here is the remarkable part. From 1783 to 1916, we had a theoretical understanding that objects like black holes could exist. The mathematics said they were possible, but we did not actually confirm the existence of a real black hole until 1971, when astronomers found Cygnus X1. That is almost 200 years from Michel's dark stars to actual observational evidence. Almost 200 years where the math was right, but we just could not see the reality yet. And this brings us to the heart of tonight's journey, because right now, in our modern era, we have equations, we have mathematical models, we have theories that predict the existence of objects far stranger than black holes. Objects that seem impossible, objects that bend our intuitions into pretzels. And maybe, just maybe, those objects are out there right now, waiting in the darkness, waiting for us to finally develop the tools to see them. Our telescopes have improved tremendously. We have detected gravitational waves. We have taken an actual photograph of a black hole's shadow. But there is still so much we cannot see. There are still so many corners of the universe that remain hidden from our instruments. And in those corners, the strangest things might be lurking. So tonight, we are going to talk about the unperceived reality, the objects that physics says should exist, or at least could exist, but that we have not found yet. Some of them might be out there right now. Some of them might form in the future. Some of them might have existed long ago, in the earliest moments after the Big Bang. And all of them are stranger than black holes. To understand these exotic objects, we first need to understand ordinary stars. And I know stars might seem boring compared to the wild things we are going to discuss. But trust me, understanding stars is like understanding the foundation of a house. You need to see the foundation before you can appreciate how strange the attic is. Our sun is a ball of gas, mostly hydrogen, with some helium mixed in. It is a big ball, about 865,000 miles across. If you could drive a car around the sun's equator at highway speeds, it would take you about 5 years. It is a lot of gas. Now, all that gas wants to do one thing. It wants to fall inward. Gravity is constantly pulling every atom in the sun toward the center. The outer layers are pressing down on the inner layers. The inner layers are pressing down on the core. It is like a pile of pillows, except instead of pillows, it is superheated plasma, and instead of a pile, it is a sphere 800,000 miles wide. So why does the sun not collapse? Why does all that gas not just crush itself into a tiny point? The answer is pressure. Specifically, radiation pressure. In the core of the sun, temperatures reach about 27 million degrees. At those temperatures, hydrogen atoms are slamming into each other so hard that they fuse together into helium. This fusion releases energy, enormous amounts of energy. That energy pushes outward, like air pushing against the inside of a balloon. And so the sun exists in a beautiful balance. Gravity pulls inward. Radiation pressure pushes outward. The two forces balance each other out, and the sun stays stable. This balance is called hydrostatic equilibrium. It is one of the most important ideas in all of astrophysics. But here is the thing about balance. Balance does not last forever. The sun is burning through its hydrogen fuel. Slowly, yes. It will take about 5 billion more years. But eventually, the fuel will run low. And when the fuel runs low, the outward pressure will decrease. And when the outward pressure decreases, gravity wins. What happens then depends on how massive the star is. For a star like our sun, the story ends relatively peacefully. The outer layers drift away into space, forming a beautiful shell of gas called a planetary nebula. The core that remains behind is something called a white dwarf. A white dwarf is strange. It is about the size of Earth, maybe a little smaller, but it contains roughly half the mass of the sun. Imagine taking all the matter in half of our sun and squeezing it into a ball the size of our planet. The density is unimaginable. A teaspoon of white dwarf material would weigh about 15 tons on Earth. At these extreme densities, something weird happens. The atoms get packed so close together that the electrons, those tiny particles that orbit atomic nuclei, start to push back against each other. This is not ordinary pressure like the pressure in a balloon. This is quantum mechanical pressure. It comes from a principle called the Pauli exclusion principle, which says that no two electrons can occupy the exact same quantum state. Think of it like this. Imagine you have a room full of people, and you tell them they all have to stand still. If there are only a few people, no problem. They each find their own spot on the floor. But if you keep adding more people, eventually the room gets crowded. People are shoulder to shoulder. They cannot all stand in the same spot. They push against each other. That pushing is kind of like what happens with electrons in a white dwarf. This electron pressure, this quantum mechanical pushing, is called degeneracy pressure, and it is what holds up a white dwarf against gravity. The star is not burning fuel anymore. There is no fusion happening in the core, but the electrons are pushing back against collapse simply because they cannot all be in the same place at the same time. White dwarfs are remarkable objects. They are the remains of stars like our Sun. They are hot when they form, glowing white hot, hence the name. But over billions of years they slowly cool down. They fade from white to yellow to red to brown, eventually becoming cold cinders drifting through space. The universe is probably full of old cold white dwarfs that we cannot see because they have stopped glowing. But white dwarfs have a limit. There is a maximum mass that electron degeneracy pressure can support. This limit is called the Chandrasekhar limit, named after the brilliant Indian-American astrophysicist Subrahmanyan Chandrasekhar, who calculated it in 1930 when he was just 19 years old. The Chandrasekhar limit is about 1.4 times the mass of our Sun. If a white dwarf somehow gains more mass than this, if it is in a binary system and is stealing gas from a companion star, for example, something dramatic happens. The electron pressure can no longer hold back gravity. The star collapses. Sometimes this collapse triggers a tremendous explosion, called a Type Ia supernova. These explosions are so bright that they can outshine entire galaxies. They are also very consistent, which makes them useful for measuring distances in the universe. Every Type Ia supernova releases roughly the same amount of energy, so by measuring how bright one appears from Earth, astronomers can figure out how far away it is. But other times, when the collapsing object is already a dense stellar core from a more massive star, the collapse leads to something else, something even denser than a white dwarf, something called a neutron star. Neutron stars form when massive stars, stars much bigger than our Sun, run out of fuel and collapse. The collapse is catastrophic. In the core of the dying star, the pressure becomes so intense that electrons are actually pushed into protons. When an electron combines with a proton, you get a neutron. And suddenly, the entire core is made of neutrons. A neutron star is tiny, only about 12 to 15 miles across. Think about that. A city like London or Los Angeles could fit on top of a neutron star. But that tiny sphere contains more mass than our entire Sun. The density is beyond comprehension. A teaspoon of neutron star material would weigh about 6 billion tons. At these densities, neutrons experience their own version of degeneracy pressure. Just like electrons in a white dwarf cannot all be in the same place, neutrons in a neutron star cannot all be in the same place either. They push back against each other due to quantum mechanics. This neutron degeneracy pressure is what holds up a neutron star against the crushing force of gravity. Neutron stars are incredible objects. They spin incredibly fast, sometimes hundreds of times per second. They have magnetic fields trillions of times stronger than Earth's. They can shoot beams of radiation from their poles, and if those beams happen to sweep past Earth, we see them as pulsing lights called pulsars. The first pulsar was discovered in 1967 and was so regular that astronomers initially thought it might be a signal from an alien civilization. They half-jokingly named it LGM-1 for little green men. But neutron stars also have a limit. Just like white dwarfs have the Chandrasekhar limit, neutron stars have something called the Tolman-Oppenheimer-Volkoff limit, or the TOV limit for short. This limit is somewhere around 2 to 3 solar masses, with our best estimate being about 2.2 solar masses. If a neutron star somehow gains more mass than this, neutron degeneracy pressure fails. The star collapses further, and when a neutron star exceeds the TOV limit, when even the quantum pressure of neutrons cannot hold back gravity, we get a black hole. the matter collapses to a point of infinite density called a singularity. Space and time curve so dramatically that nothing can escape. The event, horizon, forms, the boundary beyond which nothing returns. So we have a ladder of density. Normal stars, held up by radiation pressure. White dwarfs, held up by electron degeneracy pressure. Neutron stars, held up by neutron degeneracy pressure. And black holes, where nothing can hold back gravity anymore. But here is where things get interesting. Here is where we start to venture into the strange territory that we came here to explore. Because between neutron stars and black holes, there might be other things. Other forms of matter, other types of pressure, other ways for the universe to resist gravity's relentless pull. And beyond that ladder entirely, there might be objects that defy our expectations completely. Objects that look like black holes but are not. Objects that could only exist in a universe governed by the strange laws of general relativity and quantum mechanics. Let us start with one of the strangest. Let us talk about gravastars. The name gravastar is short for gravitational vacuum star. It was proposed in 2001 by physicists Pavel Mazur and Emil Motola, and it is one of the most mind-bending alternatives to black holes that anyone has ever imagined. Remember what happens when a massive star collapses. Gravity crushes the matter down and down and down. In the standard picture, nothing can stop this collapse. The matter falls all the way to a singularity, a point of infinite density. The event horizon forms around it. But Mazur and Motola suggested something different. They suggested that maybe, just maybe, something does stop the collapse. Not ordinary matter, not electron pressure or neutron pressure. Something much stranger. Something called vacuum energy. Vacuum energy is one of the weirdest predictions of quantum mechanics. According to quantum theory, empty space is not really empty. Even in a perfect vacuum, with no matter and no radiation, there is still energy. Particles and antiparticles are constantly popping into existence and then annihilating each other. This happens so fast that we cannot directly see it, but the energy is there. We call it the quantum vacuum, or sometimes zero-point energy. Vacuum energy is also connected to something even more mysterious, dark energy. Dark energy is the force that is causing the universe to expand faster and faster. We do not really understand what dark energy is, but one leading theory is that it is simply the energy of the vacuum itself. The vacuum pushes space apart. Now, here is the wild idea behind gravastars. What if, when a massive star collapses, instead of forming a singularity, the collapse creates a shell of matter that traps a bubble of extremely high vacuum energy inside? What if that vacuum energy, that dark energy, pushes back against the collapse and stops it? In this picture, the star does not collapse all the way to a point. Instead, it forms a hollow shell. The shell is made of incredibly dense matter, similar to the matter in a neutron star. But inside that shell, there is nothing but vacuum energy. Pure empty space, but empty space with enormous pressure. From the outside, a gravastar would look almost exactly like a black hole. It would have the same mass. It would curve space-time in the same way. Light passing near it would bend. Orbiting objects would circle it just as they would circle a black hole. Even gravitational waves from colliding gravastars might look similar to gravitational waves from colliding black holes. But there are crucial differences. A gravastar does not have a singularity. There is no point of infinite density at the center. Instead, there is just empty space. Incredibly energetic empty space, but empty space nonetheless. And a gravastar does not have a true event horizon. Well, That is not quite accurate. A gravastar has a surface that is extremely close to where the event horizon would be, so close that it would be almost impossible to tell the difference from far away. But it is a physical surface, not a one-way boundary into nothingness. Here is the really strange part. If you could somehow visit a gravastar, if you could survive the journey and make it past the outer shell of ultra-dense matter, you could float inside. You could exist in the interior. There would be no crushing gravitational force pulling you toward a central point, because there is no central point. The vacuum energy fills the interior uniformly, and its pressure balances gravity in a way that creates zero gravitational force inside. Think about that. You could float freely in the center of a gravastar. No gravity pulling you anywhere. Just you and the quantum vacuum. It is like being in the eye of the most extreme hurricane imaginable. All that chaos, all that gravity, all that matter surrounds you. But at the center, perfect stillness. Now, I should be clear. We do not know if gravastars exist. We have not found one. The idea is still theoretical, still speculative. Many physicists are skeptical. They point out that forming a gravastar would require some very specific conditions, and that ordinary black hole formation seems more likely. But here is the thing. We also cannot prove that gravastars do not exist. Our observations of black holes are still limited. We have detected gravitational waves from merging objects. We have photographed the shadows of objects at the centers of galaxies, but we have not directly seen what is at the center. We have not directly observed a singularity or confirmed that event horizons work exactly as we expect. So gravastars remain a possibility. They remain one of those objects on the menu of the strange. And if they do exist, they would completely change our understanding of what happens when gravity becomes extreme. Let us move on to something even stranger. Let us talk about white holes. A white hole is, in a sense, the opposite of a black hole. Remember, a black hole is a region of space where nothing can escape. Once you cross the event horizon, you are trapped forever. You can only fall inward. A white hole is a region of space where nothing can enter. Matter and light can only come out. If you tried to approach a white hole, you would be pushed away. The closer you got, the harder you would be pushed. You could never cross the boundary into the interior. Now, where does this idea come from? It comes directly from the mathematics of general relativity. When Schwarzschild solved Einstein's equations in 1916, he found a solution that describes a black hole. But that solution has a twin. The mathematics are symmetric in a way that allows for both black holes and white holes. Let me try to explain this with an analogy. Imagine a cone, an ice cream cone, like you might get at a carnival on a summer day. Now imagine an ant walking on that cone. If the ant is on the outside of the cone and starts walking downward toward the point, gravity will help it along. It will slide down easily, but if it tries to climb back up, it will struggle. The slopes get steeper and steeper near the point. A black hole is like the inside of that cone. Once you pass a certain boundary, once you go past the event horizon, you can only go down. You can only fall toward the singularity. No matter how hard you try, you cannot climb back out. Now flip the cone over. Or better yet, imagine a traffic cone, the kind you see on the road at construction sites. A traffic cone is open at the bottom. If our ant is inside the traffic cone, near the point at the top, it can only go down. It can only slide out through the opening at the bottom. It cannot climb up toward the point. That is kind of like a white hole. Things inside can only come out. Things outside cannot get in. The mathematics of general relativity says that both kinds of cones are possible. Both kinds of boundaries can exist. There is an even more interesting way to visualize this. Physicists use something called a Penrose diagram, named after the brilliant mathematician and physicist Roger Penrose. A Penrose diagram is a special kind of map that shows the structure of space-time in extreme situations. In a Penrose diagram of a black hole and white hole system, you see 4 regions. Region 1 is our universe, the normal space-time where you and I live. Region 2 is the interior of a black hole, the region behind the event horizon where everything falls toward the singularity. Region 3 is the interior of a white hole, the region from which things can only emerge. And Region 4 is something truly mind-bending, another universe, a parallel universe that exists on the other side of the singularity. Now, here is the important thing to understand. In the simplest mathematical model, a non-rotating, eternal black hole, you cannot actually travel to Region 4. You cannot use a black hole as a portal to another universe. The singularity gets in the way. You would be crushed by infinite gravitational forces before you could reach the other side. But this is where things get really interesting, because most real black holes are not simple. Most real black holes spin. When a star collapses to form a black hole, it almost always has some rotation. Stars spin because the clouds of gas that formed them were spinning. And that angular momentum, that rotational energy, does not go away. It gets concentrated as the star collapses. So the resulting black hole spins too. And spinning changes everything. A spinning black hole is described by a different mathematical solution, called the Kerr solution, after the New Zealand mathematician Roy Kerr, who discovered it in 1963. The Kerr solution is more complicated than Schwarzschild's original solution, and it has some very strange properties. For one thing, a spinning black hole does not have a point singularity. Instead, it has a ring singularity. The matter collapses not to a single point, but to a ring shape. This ring exists at the center of the black hole, spinning at incredible speeds. But here is the really wild part. If you approach a ring singularity from the right angle, if you come in along the axis of rotation, you might be able to pass through the ring without hitting it. And on the other side of that ring, according to the mathematics, there might be another region of space-time, another universe perhaps, or maybe a different part of our own universe. In other words, a spinning black hole might be a portal, not a simple portal like a doorway, but a twisted, dangerous passage through the fabric of space-time itself. This is where wormholes come in. A wormhole is a hypothetical tunnel through space-time, connecting 2 distant regions. The black hole entrance, the white hole exit, and the tunnel between them would form what is called an Einstein-Rosen bridge. This idea was first proposed by Einstein himself, along with his colleague Nathan Rosen, back in 1935. The mathematics says such bridges could exist, but the mathematics also says they would be extremely unstable. Any matter or even radiation passing through the wormhole might cause it to collapse instantly. The tunnel would pinch shut, trapping or destroying anything inside. Some physicists have speculated that exotic matter with negative energy density, might be able to stabilize a wormhole. But we have never observed such matter. We do not know if it exists. For now, stable, traversable wormholes remain in the realm of science fiction. But here is a thought to carry with you. The mathematics of general relativity allows for these structures, just like the mathematics allowed for black holes decades before we found them. just like the mathematics allowed for gravitational waves long before we detected them. The equations are telling us something. Maybe not about objects that exist right now, but about possibilities, about what the universe could contain. And maybe, somewhere out there, in some distant corner of the cosmos, white holes are erupting, matter and energy pouring out from nowhere in defiance of everything we expect. We do not know. We have not found them, but the math says they are possible. And history has taught us to take the math seriously. Let us go deeper into the idea of spinning black holes, because the story gets stranger the more closely we look. When a black hole spins, it does not just spin in place like a top. It actually drags the space-time around it. Imagine stirring a cup of honey with a spoon. The honey near the spoon gets pulled along, swirling in circles. Something similar happens with space-time around a spinning black hole. This effect is called frame dragging, and it creates a region around the black hole called the ergosphere. The ergosphere is not quite like the event horizon. You can escape from the ergosphere, but while you are inside it, you cannot stand still. You are forced to rotate along with the black hole, whether you want to or not. Space-time itself is flowing, and you flow with it. The ergosphere has some bizarre properties. For one thing, it is theoretically possible to extract energy from a spinning black hole by exploiting the ergosphere. This process was described by Roger Penrose and is called the Penrose process. You send an object into the ergosphere, it splits into two pieces. One piece falls into the black hole, and the other piece escapes with more energy than it started with. The extra energy comes from the rotation of the black hole itself. You are essentially stealing the black hole's spin. But let us focus on what happens when you go deeper, when you cross the event horizon of a spinning black hole. You enter a very strange region. Space and time swap their roles in a certain sense. In normal space, you can move freely in any spatial direction, but you can only move forward in time. Inside the event horizon of a non-spinning black hole that flips, time behaves like space used to, and one spatial direction behaves like time. You are pulled inexorably toward the singularity, just as you are normally pulled inexorably toward the future. But in a spinning black hole, there is a second horizon. It is called the inner horizon, or the Cauchy horizon. And when you cross that inner horizon, something remarkable happens. The strangling grip of the singularity loosens. Space unwarps, in a sense. The pull toward the center becomes less absolute. Inside the inner horizon, you find the ring singularity. And as I mentioned earlier, this ring is not like the point singularity of a simple black hole. It is a doorway, or at least the mathematics suggests it might be. If you pass through the ring, carefully avoiding the edges where gravity becomes infinite, you might emerge into another region of space-time. This other region is sometimes called the antiverse or the mirror universe in the context of Penrose diagrams. It is region 4, the parallel reality on the other side. According to the mathematics, this region has strange properties. Gravity might work differently there. The arrow of time might point in an unexpected direction. It would be a truly alien place. But I should add some important caveats here. The mathematical solutions that describe these possibilities are idealized. They assume perfect conditions that probably do not exist in real black holes. Real black holes are messy. They formed from collapsing stars, which means infalling matter and radiation. All that stuff piling up near the inner horizon might create instabilities. The inner horizon might be a very dangerous place, potentially fatal for any traveler. Some physicists believe the inner horizon would be blasted by a wall of lethal radiation. Accumulated light and matter that has been piling up since the black hole formed. Others suggest the inner horizon might actually be a physical singularity itself, where the mathematics breaks down and our predictions fail. So while the theoretical possibility of travel through spinning black holes is fascinating, we should not book our tickets just yet. The universe might have other plans for what happens in those extreme regions. Still, the very fact that these structures appear in our equations is remarkable. The mathematics of general relativity is telling us that space-time is far more flexible, far more strange than our everyday experience would suggest. Black holes are not just cosmic vacuum cleaners, sucking up everything nearby. They are intricate structures with layers and horizons and regions, like cities with neighborhoods and districts. And this brings us back to white holes. Remember, white holes are the time-reversed version of black holes. If a black hole is a region where things can only fall in, a white hole is a region where things can only come out. In the Penrose diagram of an eternal black hole, the white hole exists in the past. It is region 3, the region from which matter and energy emerge. If we could somehow run the universe backward in time, black holes would become white holes, absorbing nothing and ejecting everything they had ever swallowed. But could white holes exist in our universe, running forward in time, right now? Could there be cosmic fountains out there spewing matter and energy into space? At first glance, this seems unlikely. After all, we know how black holes form. Massive stars collapse. Gravity overwhelms all other forces. The matter falls inward. But how would a white hole form? What process would create a region that only ejects matter? One possibility involves something called loop quantum gravity. This is a theoretical approach to combining general relativity with quantum mechanics. In loop quantum gravity, space-time itself is quantized. It comes in tiny discrete units, much like matter comes in atoms. And these quantum effects might prevent singularities from forming. According to some models in loop quantum gravity, when a black hole forms, the collapsing matter does not actually reach a true singularity. Instead, quantum effects create a bounce. The matter compresses down and down until it reaches an incredibly tiny size, something called the Planck scale, and then it rebounds. It bounces back outward. But here is the catch. From our perspective, outside the black hole, this bounce takes an unimaginably long time. Black holes are not just holes in space, they are holes in time too. Time passes differently near a black hole. For someone falling in, the trip to the center happens quickly. But for someone watching from far away, the infalling traveler seems to slow down, getting dimmer and more redshifted, never quite reaching the horizon. Similarly, the quantum bounce that might happen at the center of a black hole could be extremely fast from the perspective of the bouncing matter. But from our outside perspective, it would take an astronomically long time. Longer than the current age of the universe, perhaps. Longer than the lifespan of most black holes. But eventually, according to this picture, the bounce would complete. The black hole would transform into a white hole. All the matter that fell in, plus all the information about what fell in, would come bursting back out. This idea connects to something called the black hole information paradox. When matter falls into a black hole, where does the information about that matter go? According to quantum mechanics, information should be conserved. It should never truly be destroyed. But black holes seem to eat information and never give it back. Stephen Hawking proposed that black holes slowly evaporate over time through a process now called Hawking radiation. Tiny particles escape from near the event horizon due to quantum effects. Over incredibly long timescales, This radiation causes the black hole to shrink and eventually disappear. But Hawking radiation seemed to be random. It did not seem to carry any information about what fell into the black hole. This created a paradox. If the black hole evaporates completely, where did the information go? The white hole picture offers a possible answer. Maybe the information is not destroyed. Maybe it is just stored, waiting. When the quantum bounce completes, when the black hole becomes a white hole, all that stored information comes flooding back out. The universe's accounting books balance. Nothing is truly lost. This is a beautiful idea, but it remains speculative. We have no direct evidence that quantum gravity works this way. We have no observations of white holes, but the mathematics is suggestive. The pieces fit together in an elegant way, and that elegance is often a sign that we are on the right track. Let us move on to another exotic possibility, the Big Bounce. According to the standard model of cosmology, our universe began with the Big Bang. About 13.8 billion years ago, everything we can see, all the matter, all the energy, all of space and time, was compressed into an incredibly hot, dense state. Then it expanded rapidly. The universe cooled, particles formed, then atoms, then stars and galaxies. And here we are, looking back at that ancient fireball. But what happened before the Big Bang? This is a question that has puzzled physicists and philosophers for as long as we have known about the Big Bang. The standard answer is that the question might not even make sense. If time itself began with the Big Bang, then there was no before. Asking what happened before the Big Bang might be like asking what is north of the North Pole. But some physicists are not satisfied with that answer, and loop quantum gravity, along with other approaches to quantum gravity, offers an alternative picture. What if the Big Bang was not the beginning? What if it was a bounce? In this picture, our universe is not the first. Before the Big Bang, there was another universe. That universe was contracting. It was getting smaller and denser, just as our universe is currently expanding and getting less dense. Eventually, that contracting universe reached an incredibly compressed state. In classical general relativity, that compression would lead to a singularity. A point of infinite density where the laws of physics break down. But if quantum gravity prevents singularities, if there is always a bounce when things get too compressed, then that previous universe did not end in a singularity. Instead, it bounced. And that bounce was what we call the Big Bang. Our universe, in this picture, is the phoenix that rose from the ashes of the previous universe. The Big Bang was a transition, not a beginning. It was the moment when contraction became expansion, when falling became rising, when a cosmic black hole turned into a cosmic white hole. This idea has profound implications. It means the universe might be eternal, in a sense. Not eternal in a static way, but eternal in a cyclical way. Universes expand, then contract, then bounce, then expand again. An endless cosmic heartbeat, stretching forward and backward in time forever. It also means that information from the previous universe might have survived the bounce. Subtle patterns in the cosmic microwave background, the afterglow of the Big Bang, might contain echoes of that earlier cosmos. Astronomers have actually looked for such echoes, though the results so far have been inconclusive. But let us step back from these grand cosmic speculations and return to the specific exotic objects that might exist in our universe right now. I have mentioned gravitar stars. I have mentioned white holes. But there are other possibilities too. Let me tell you about a few more. First, there are quark stars. I mentioned that neutron stars are made of neutrons, held up by neutron degeneracy pressure. But neutrons are not fundamental particles. They are made of smaller particles called quarks. Specifically, each neutron contains 3 quarks, held together by the strong nuclear force. Under normal conditions, quarks are never found alone. They are always confined inside protons, neutrons, or other composite particles. This confinement is a fundamental property of the strong force. It is called color confinement because the strong force is described using a property called color charge, which has nothing to do with actual colors, but is a useful mathematical analogy. But at the extreme densities inside a neutron star, things might be different. The pressure might be so intense that the neutrons themselves break apart. The quarks might become free, or at least free to move around within a larger region. They would still be confined by the strong force, but not to individual neutrons. Instead, they would form a kind of quark soup, or quark matter. A neutron star that has undergone this transition would be called a quark star. Its interior would not be made of neutrons at all, but of free quarks swimming in a sea of gluons, the particles that carry the strong force. The outer layers might still look like a normal neutron star, but the core would be fundamentally different. Quark stars, if they exist, would be denser than neutron stars. They might be more compact, smaller in size for the same mass. This could affect the gravitational waves they produce when they collide. It could affect how they spin down over time. Astronomers are looking for signatures of quark stars, but so far we have not definitively identified one. There is also an even more exotic possibility: strange quark matter. Under most conditions, quarks come in 2 varieties called up quarks and down quarks. These are the quarks that make up protons and neutrons. But there are other types of quarks too. One of them is called the strange quark. Some physicists have proposed that matter made of roughly equal parts up, down, and strange quarks might be more stable than ordinary matter. This hypothetical substance is called strange quark matter, and it could have remarkable properties. If strange quark matter exists, it might form strange stars. These would be similar to quark stars, but made of strange quark matter instead of ordinary quark matter. Strange stars could potentially be even more compact than quark stars. They might have no crust at all, just bare quark matter all the way to the surface. Even more intriguingly, strange quark matter might be contagious. If a piece of strange quark matter came into contact with ordinary matter, it might convert that ordinary matter into more strange quark matter. A single strange quark nugget, falling onto a neutron star, could potentially convert the entire neutron star into a strange star. This has led some physicists to worry about a scenario called the Strangelay hypothesis. A Strangelay is a small chunk of strange quark matter. If Strangelays exist, and if they are stable, and if they convert ordinary matter on contact, then they could be dangerous. A strangelet hitting Earth could theoretically start a chain reaction, converting the entire planet into strange matter. Fortunately, this scenario seems very unlikely. We have no evidence that strangelets exist. We have no evidence that strange quark matter is more stable than ordinary matter. And even if it is, the conversion process might be slow or might require special conditions. Earth has been bombarded by cosmic rays for billions of years without turning into strange matter, which suggests that naturally occurring strangelets are either very rare or do not exist at all. But the possibility remains a fascinating example of how exotic physics could have very real consequences. The universe might contain materials that we cannot even imagine, with properties that would seem like magic to us. Let me tell you about one more exotic object, the fuzzball. Fuzzballs come from string theory. a theoretical framework that attempts to describe all the fundamental forces and particles of nature using tiny vibrating strings. String theory is mathematically complex and has not yet been experimentally verified, but it makes some interesting predictions about black holes. In string theory, black holes are not empty inside. They are not singularities surrounded by event horizons. Instead, they are tangles of strings and other extended objects called brains. The interior is filled with this stringy stuff, like a ball of cosmic yarn. The surface of a fuzzball is not a sharp boundary like the event horizon of a classical black hole. It is fuzzy, hence the name. There is no exact point where the fuzzball begins. Instead, the strings and brains gradually become denser and more tangled as you approach the center. Fuzzballs solve the information paradox in a different way than white holes. In the fuzzball picture, information that falls into a black hole is stored on the strings and brains. It is not hidden behind an event horizon. It is encoded on the surface of the fuzzball, like data on a cosmic hard drive. When the fuzzball evaporates through Hawking radiation, that information is released back into the universe. The fuzzball picture is still controversial. Many physicists are skeptical of string theory in general and fuzzballs in particular, but it represents another possibility, another way that the universe might resolve the puzzles posed by black holes. What strikes me about all these possibilities is how creative they are. Physicists are not just accepting black holes as the final answer. They are pushing, questioning, imagining alternatives. They are asking, what if the universe is stranger than we thought? What if there are objects out there that we have not even dreamed of yet? And they are using mathematics as their guide. Just as Michel and Schwarzschild used mathematics to predict black holes long before we found them, modern physicists are using mathematics to predict gravastars and white holes and quark stars and fuzzballs. Some of these predictions might be wrong, some might be right. We will not know for sure until we develop better ways to observe the most extreme environments in the cosmos. But one thing seems certain. The universe is not simple. It is not boring. It is a place of endless surprises, endless mysteries, endless wonders. And we are lucky enough to live in a time when we can explore those mysteries, even if only through the lens of mathematics and the signals of distant light. Let us take a breath here. We have covered a lot of ground. We have talked about the ladder of density, from normal stars to white dwarfs, to neutron stars to black holes. We have explored gravastars, objects with cores of vacuum energy that mimic black holes without having singularities. We have discussed white holes, the time-reversed counterparts of black holes that might exist somewhere in the universe. We have looked at spinning black holes and the strange possibilities they present, including ring singularities and potential gateways to other regions of space-time. We have touched on loop quantum gravity and the idea that quantum effects might prevent singularities from forming, leading to bouncing black holes that eventually become white holes. We have considered the Big Bounce, the possibility that our Big Bang was not a beginning but a transition from a previous contracting universe. And we have briefly mentioned quark stars, strange stars, and fuzzballs, each representing a different way that matter might behave under extreme conditions. But we are not done yet. There is still more to explore. Let us go deeper into some of these ideas. Let us ask harder questions. Let us see just how strange the universe might be. One of the most tantalizing aspects of these exotic objects is what they tell us about the nature of space-time itself. We tend to think of space as a stage, a backdrop against which events happen. Objects move through space. Time flows forward. But general relativity tells us that space and time are not just a stage. They are active participants in the drama. They can bend and stretch and twist. They can have holes. They can connect in unexpected ways. Let me try to explain this with an analogy. Imagine you are an ant living on a piece of paper. You can crawl forward and backward. You can crawl left and right, but you cannot crawl up or down off the paper. The paper is your entire universe. Your world is two-dimensional. Now imagine someone takes that paper and folds it in half. The two halves of the paper are now very close together, even though, from your ant perspective, they still seem far apart. If you could somehow burrow through the paper, you could create a shortcut. You could travel between two distant points on the paper much faster than by crawling along the surface. This is in essence what a wormhole might be, a fold in space-time, a tunnel that connects two distant points, allowing travel between them without traversing the space in between. But here is the thing about folding paper. You need something outside the paper to do the folding. You need that third dimension. The paper cannot fold itself. With space-time, the situation is more subtle. Space-time can curve and connect in ways that do not require an external higher dimension. The geometry can be intrinsically different. A wormhole can exist as a feature of space-time itself, not as something embedded in a larger space. This is mathematically possible. The equations of general relativity allow for it, but making it physically happen is another matter entirely. The simplest wormholes, the ones that Einstein and Rosen first described, are unstable. They would collapse before anything could pass through. To keep a wormhole open, to stabilize it, you would need something very unusual. You would need exotic matter. Exotic matter is a hypothetical substance with negative energy density. Normal matter has positive energy density. A rock sitting on your desk, the air in your lungs, the light from the sun, all have positive energy. But exotic matter would have energy that is somehow less than zero. This sounds impossible, and in most contexts it is. We do not encounter negative energy in our daily lives, but there are situations in physics where something like negative energy can occur, at least locally and temporarily. The Casimir effect is one example. If you take two uncharged metal plates and place them very close together in a vacuum, they will attract each other. This happens because of quantum fluctuations in the vacuum between the plates. The plates restrict which quantum fluctuations can occur, and this restriction creates a kind of negative energy density between them. The Casimir effect is real. It has been measured. It is tiny, but it exists. And some physicists have speculated that similar effects, scaled up to cosmic proportions, might be able to stabilize a wormhole. But we are talking about scaling up by an enormous factor. The Casimir effect between laboratory plates involves incredibly tiny energies. Stabilizing a wormhole large enough for a person, or even a spacecraft, to pass through would require amounts of negative energy that we cannot currently imagine producing. Still, the theoretical possibility exists, and that is what makes this so intriguing. The universe seems to allow for wormholes, at least in principle. Whether nature actually creates them is a question we cannot yet answer. There are other constraints on wormholes too. Even if you could stabilize one, there are questions about whether it could actually be used for faster-than-light travel. Some calculations suggest that as soon as you try to send anything through a wormhole, including light, the wormhole might become unstable anyway. The very act of traversing it might destroy it. There are also strange issues with causality. If a wormhole connects 2 points in space, it might also connect 2 points in time. Depending on how the wormhole is oriented, and how it moves through space, it might be possible to use it to travel backward in time. And that opens up all the famous paradoxes of time travel: the grandfather paradox, the bootstrap paradox, all the headaches that physicists have been arguing about for decades. Some physicists believe that the universe has a kind of cosmic censorship mechanism, something that prevents paradoxes from occurring. Maybe wormholes that would allow time travel always collapse before they can be used. Maybe the laws of physics simply do not allow the creation of such wormholes in the first place. We do not know for sure. But even without traversable wormholes, even without the prospect of cosmic shortcuts, the idea of connected spacetimes is fascinating. It tells us that the universe might be more interconnected than it appears. Distant regions might be linked by invisible threads of geometry. The fabric of spacetime might have holes and handles and tunnels that we cannot see. Let us talk more about topology. Topology is the branch of mathematics that studies the shapes of things but not their sizes or distances. In topology, a coffee cup and a donut are the same shape because you can smoothly deform one into the other. They both have one hole. A sphere and a football are the same shape topologically because neither has any holes. The topology of spacetime tells us how the universe is connected at a fundamental level. Our everyday experience suggests that space is simple and flat, like an infinite three-dimensional grid, extending in all directions. But general relativity allows for other possibilities. Space could be curved. It could loop back on itself. If you traveled in a straight line long enough, you might end up back where you started, like an ant walking around a balloon. The universe could be finite in size, but have no edges, no boundaries. Space could also have holes. Not holes in the sense of empty regions, but holes in the topological sense. Wormholes are one example, but there could be others. There could be regions of space that are simply not connected to the rest. Islands of space-time isolated from everything else. These possibilities are allowed by the mathematics. Whether they are realized in our actual universe is an open question. So far, all observations are consistent with a simple, simply connected space-time. But we have only explored a tiny fraction of the cosmos. There could be surprises waiting. Let me return to white holes for a moment, because there is a version of the white hole idea that connects to something we might actually observe. Imagine a black hole that formed long, long ago, perhaps in the early universe, shortly after the Big Bang. Over billions of years, this black hole has been slowly evaporating through Hawking radiation. It has been getting smaller and smaller. Its mass has been decreasing. Now, according to the bounce picture I described earlier, when the black hole gets small enough, when it reaches the Planck mass, quantum effects take over. The singularity never quite forms. Instead, the collapsing matter bounces back, and the black hole becomes a white hole. But here is the interesting part. The bounce might happen very quickly from the perspective of the matter itself, but very slowly from our outside perspective. The original black hole might have formed billions of years ago. The bounce might be happening right now, or it might have happened already, and we just have not noticed yet. What would we see when a black hole completes its bounce and becomes a white hole? We might see a sudden burst of energy. All the matter and radiation that fell into the black hole over its entire lifetime might come erupting out in an instant. Some physicists have speculated that fast radio bursts, mysterious millisecond pulses of radio waves that we have been detecting from distant galaxies, might be the signatures of bouncing black holes. The energy would be enormous. The burst would be brief but brilliant, and then it would be over. The white hole would have expelled everything it had stored. This is a fascinating possibility, though it remains unproven. Fast radio bursts are still not fully understood. They might have other explanations, involving magnetars or other extreme objects. But the white hole hypothesis is one possibility on the table. Let us take a step back and think about what all of this means for our understanding of the universe. When we look at the night sky, we see stars and planets, galaxies and nebulae. We see light that has traveled for billions of years to reach us. We see a universe that is vast and ancient and beautiful. But what we see is only part of the story. Our eyes and our telescopes can only detect certain kinds of light. We cannot see dark matter, even though it makes up most of the mass in galaxies. We cannot see dark energy, even though it is driving the accelerating expansion of the universe. We cannot see black holes directly. We can only infer their presence from their effects on nearby matter. And beyond what we cannot see, there are things we cannot even imagine. Objects and structures and phenomena that our theories predict but that we have not yet found. Gravitar stars and white holes and quark stars. Wormholes and fuzzballs and strange quark matter. Our understanding of the universe is like a map drawn by explorers who have only seen a small part of the territory. We have charted the coastline. We have surveyed some of the mountains and rivers. But there are vast interiors that remain blank, marked only with the note, "Here be dragons." Except in our case, the dragons might be real. They might be gravitational vacuum stars hovering at the edge of the possible. They might be ancient black holes reaching the end of their long bounces. They might be structures in space-time that connect distant corners of the cosmos. I find this both humbling and inspiring. Humbling because it reminds me how little we truly know. Inspiring because it suggests how much is left to discover. Think about the history of astronomy. A few hundred years ago, people thought the sun went around the earth. They thought the stars were fixed lights on a celestial sphere. They thought the universe was small and centered on us. Then we discovered that the earth goes around the sun, that the sun is just one star among billions in the Milky Way galaxy, that the Milky Way is just one galaxy among billions in the observable universe, that the universe is expanding, that it began in a hot, dense state we call the Big Bang. Each of these discoveries was a revolution. Each one forced us to revise our picture of reality, and there is no reason to think the revolutions are over. The exotic objects we have been discussing might be the next revolution. Gravastars might force us to rethink what we know about extreme gravity. White holes might reveal that the arrow of time is more flexible than we thought. Wormholes might show us that space-time has a topology we never imagined. Or maybe all these ideas are wrong. Maybe the universe is simpler than the mathematics suggests. Maybe black holes are just black holes, with singularities at their centers and event horizons that work exactly as predicted. Maybe there are no alternatives, no exotic objects, no surprises. But I do not think so. The universe has consistently proven to be stranger than we expected. Every time we have developed new tools, new telescopes, new detectors, we have found things we did not anticipate. Pulsars, quasars, gamma-ray bursts, dark energy, the cosmic microwave background. The pattern suggests that more surprises are coming. The blank spaces on our map are not empty. They are full of things we have not discovered yet. And that is a beautiful thought to hold as we drift towards sleep. The universe is not finished revealing itself. The story is not over. There are chapters yet to be written, and we might be the ones who write them. Let me tell you about one more aspect of these exotic objects, how we might actually detect them. I have mentioned several times that gravastars and white holes and other exotic objects would look very similar to black holes from a distance. They would have the same mass. They would curve space-time in the same way. Objects would orbit them just as they would orbit black holes. So how could we tell the difference? One possibility is gravitational waves. When two massive objects spiral together and merge, they send ripples through space-time. These ripples, gravitational waves, carry information about the objects that created them. The shape of the waves, their frequency, their amplitude, all depend on what exactly is merging. We have been detecting gravitational waves since 2015, when the LIGO Observatory made its first direct observation. Since then, we have detected dozens of events. Most of them seem consistent with black hole mergers. But the precision of our measurements is still limited. We might be missing subtle differences. If gravastars exist, they might produce slightly different gravitational wave signatures than black holes. The waves might have different frequencies near the moment of merger. There might be echoes, reflections from the surface of the gravastar that would not occur with a true event horizon. Scientists are actively looking for these echoes. So far, the evidence is inconclusive. Some analyses have found hints of echoes in the LIGO data. Other analyses have found nothing. The debate continues. Another possibility is observations of the black hole shadow. The Event Horizon Telescope, which famously imaged the supermassive object at the center of the galaxy M87, showed a dark region surrounded by a bright ring of glowing gas. That dark region is the shadow of the event horizon. If the object at the center of M87 is actually a gravastar or some other exotic object, its shadow might look slightly different. The edge of the shadow might be sharper or fuzzier. The shape might be subtly distorted. As we improve our ability to image these shadows, we might be able to detect such differences. There are also possibilities involving light that falls into the object and comes back out. For a true black hole, light that crosses the event horizon never returns. But for a gravastar, light might reflect off the inner structure and escape. There could be faint echoes, delayed reflections that arrive at our telescopes long after the original light signal. Detecting such echoes would be incredibly difficult. The signals would be faint. They would be buried in noise. But the payoff would be enormous. If we found evidence that black holes are not really black holes, that they are something else entirely, it would revolutionize our understanding of gravity. White holes present different observational challenges. If a white hole is erupting somewhere in the universe, we might see it as a sudden burst of energy. But how would we distinguish a white hole eruption from a supernova, or a gamma ray burst, or some other violent cosmic event? One clue might be the spectrum of the light. White holes would presumably release the accumulated matter and energy from their black hole phase. That matter might include unusual elements, unusual proportions of matter and antimatter, or other signatures that would not be expected from ordinary astronomical events. Another clue might be the timing and location. A white hole eruption would occur at the site of an old black hole. If we could trace the eruption back to a location where we had previously detected a black hole, that would be strong evidence. But these are speculative ideas. We do not know exactly what a white hole eruption would look like because we have never seen one. We are groping in the dark, looking for something we have only imagined. This is the nature of exploration. You do not always know what you are looking for until you find it. The universe has a way of surprising us. The key is to keep looking, keep observing, keep questioning. And that is what astronomers are doing. Right now, as we speak, telescopes around the world and in space are gathering light from distant objects. Gravitational wave detectors are listening for the rumbles of cosmic collisions. Computers are crunching through mountains of data, looking for patterns that might reveal something new. Somewhere in that data, there might be evidence of exotic objects. Somewhere, there might be a signal that does not quite fit our expectations. A gravitational wave with an unexpected echo. A burst of light with an unusual spectrum. An image that shows something we have never seen before. When that discovery comes, when we finally confirm the existence of something truly strange, it will be a moment to remember. It will be the moment when our map gets a little bit bigger, when another blank space gets filled in, when we learn something new about the universe we call home. I think about the scientists who will make that discovery. They might be working late at night, staring at their computer screens, sipping cold coffee. They might see a blip in the data and think it is a glitch. They might check it again and again, unable to believe what they are seeing. And then the realization will dawn. This is real. This is something new. This changes everything. I envy them in a way. I envy the thrill of that discovery. But I also know that we are all part the journey. Everyone who looks up at the stars with wonder, everyone who asks questions about the universe, everyone who refuses to accept that we know everything there is to know. We are all explorers, in our own way. The universe rewards curiosity. It rewards those who look deeper, who push further, who refuse to be satisfied with easy answers. And the exotic objects we have been discussing tonight are a reminder of how much is left to explore. So as you drift towards sleep, let these ideas float through your mind. Gravastars with their cores of dark energy, white holes erupting matter into the void, wormholes threading through the fabric of space, spinning black holes with their ring singularities and their hints of other universes. These are not just science fiction. They are possibilities, written in the language of mathematics, waiting to be confirmed or ruled out by the hard work of observation. They are chapters in a story that is still being written, and you are part of that story. We all are. Every question we ask, every moment of wonder we feel, every night we spend gazing at the stars, we are participating in the great human project of understanding the cosmos. It is a project that has no end. The universe is infinite in its strangeness, infinite in its beauty. We will never finish exploring it. But that is not a reason for despair. It is a reason for joy. There will always be something new to discover. There will always be another mystery to unravel. There will always be another exotic object, another strange phenomenon, another surprise waiting just beyond the edge of our knowledge. And that is a wonderful thing. Let us return to the idea of loop quantum gravity and explore it more deeply, because this theoretical framework might hold the key to understanding what really happens inside black holes. General relativity is our best theory of gravity. It describes how mass and energy curve space-time, and how that curvature guides the motion of objects. It has been tested countless times and has passed every test with flying colors. From the bending of starlight during solar eclipses to the precise orbits of GPS satellites, general relativity works. But general relativity has a problem. It predicts its own breakdown. At the center of a black hole, according to general relativity, the curvature of space-time becomes infinite. All the mass is compressed to a single point of zero size and infinite density. This point is called a singularity. Singularities are not just extreme. They are places where the equations stop making sense, dividing by zero. Infinity appearing where we expect a finite answer. These are signs that the theory is missing something. They are signs that we need a deeper theory, one that can handle these extreme conditions. Quantum mechanics is our best theory of the very small. It describes atoms and electrons and photons. It tells us that energy comes in discrete packets, that particles can be in multiple places at once until you observe them, that there is fundamental uncertainty built into the fabric of reality. Quantum mechanics has also been tested countless times and has passed every test. It underlies all of modern electronics, all of chemistry, all of our understanding of matter at the smallest scales. But quantum mechanics and general relativity do not get along. They are written in different mathematical languages. They make different assumptions about how the universe works. When you try to combine them, the equations often spit out nonsense. Infinities pile on infinities. This is the central problem of modern physics: how to reconcile quantum mechanics with general relativity, how to create a theory of quantum gravity. Loop. Quantum gravity is one attempt to solve this problem. It was developed in the 1980s and 90s by physicists including Abhay Ashtekar, Lee Smolin, and Carlo Rovelli. It takes the ideas of general relativity seriously, that space-time itself is dynamic and can curve, and tries to apply quantum principles to space-time itself. In loop quantum gravity, space-time is not a smooth continuum. It is granular. It comes in discrete chunks, like the atoms that make up matter. These chunks are incredibly tiny, about 10 to the minus 35 meters across. This is called the Planck length, and it is the scale at which quantum effects in gravity are expected to become important. At scales much larger than the Planck length, space-time appears smooth and continuous, just as a piece of cloth appears smooth from a distance, even though it is made of individual threads. But at the Planck scale, the threads become visible. Space-time has structure. This granularity has profound consequences. One of the most important is that singularities might not exist. Remember what happens in general relativity when matter collapses into a black hole. The matter falls inward, getting denser and denser. Space-time curves more and more sharply, and eventually, if nothing stops the collapse, everything reaches a single point of infinite density. But in loopy quantum gravity, something does stop the collapse. When the matter approaches the Planck density, when space-time itself is being compressed to the scale of its own granularity, new effects kick in. The quantum structure of space resists further compression. There is a kind of quantum pressure that pushes back against gravity. This is not ordinary pressure like the pressure in a gas. It is not degeneracy pressure like the pressure in a white dwarf or neutron star. It is a new kind of pressure that arises from the quantum nature of space-time itself. And this pressure creates a bounce. The collapsing matter does not reach a singularity. Instead, it bounces. It starts expanding again. The black hole transforms into a white hole. This is a beautiful picture. It takes two puzzles, the puzzle of singularities and the puzzle of white holes, and suggests that they are connected. White holes are not separate objects that have to form somehow. They are the natural outcome of what happens when black holes reach the Planck scale. But there is a complication. The bounce happens very quickly from the perspective of the bouncing matter. But from our perspective, outside the black hole, time is severely distorted. The closer you are to the event horizon, the slower time passes relative to the outside world. Because of this time dilation, the bounce that takes an instant for the matter inside can take an extremely long time for observers outside. How long? Possibly longer than the current age of the universe. Possibly much, much longer. This means that even if the loop quantum gravity picture is correct, even if every black hole will eventually bounce and become a white hole, we might not see it happen. The black holes we observe today might still be in their black hole phase, slowly progressing toward a bounce that is billions or trillions of years in the future. But there is a caveat to this caveat. The smallest black holes would bounce the fastest. The time delay scales with the size of the black hole. A tiny black hole, one that formed in the early universe and has since evaporated down to a very small mass, might be bouncing right now, or it might have already bounced. These tiny bouncing black holes might produce observable signals, brief flashes of energy as they transition from black hole to white hole. Strange particles ejected from the bounce. Gravitational wave signatures unlike anything from ordinary black hole mergers. Astronomers are looking for such signals. They are scanning the sky for unexplained flashes. They are searching for exotic particles in cosmic ray detectors. They are combing through gravitational wave data for unusual patterns. So far, nothing definitive has been found, but the search continues. And every observation that comes back negative tells us something too. It places limits on how many tiny black holes might exist. It constrains the properties that white hole eruptions might have. Science advances both by what we find and by what we do not find. Let us think about the implications of loop quantum gravity for our understanding of the Big Bang. According to the standard cosmological model, the universe began with a singularity. Everything we see today, all the galaxies and stars and planets, all the matter and energy, was once compressed into a state of infinite density. Then it expanded, the Big Bang. But if singularities do not actually exist, if quantum effects prevent them from forming, then the Big Bang singularity might not be real either. The universe might not have begun with a moment of infinite density. Instead, the universe might have bounced. Before our current expanding phase, there might have been a previous contracting phase, a universe much like ours, full of galaxies and stars, but shrinking instead of growing. As that universe contracted, it got denser and hotter. Eventually, it reached the Planck density. And then, instead of collapsing to a singularity, it bounced. It started expanding again. That bounce was what we call the Big Bang. This picture is sometimes called the Big Bounce. It suggests that our universe did not come from nothing. It came from a previous universe. And that previous universe might have come from a universe before it. The cosmic heartbeat might extend infinitely into the past, an endless cycle of expansion and contraction. This is a staggering idea. It means the universe might be eternal, not in the sense of lasting forever into the future, though that might be true too. Eternal in the sense of having no beginning, no first moment, no creation from nothing. Of course, this picture raises its own questions. If the universe has been bouncing forever, how did it start bouncing in the first place? Where did the original energy come from? These are deep questions that loop quantum gravity does not fully answer. But perhaps they are the wrong questions. Perhaps asking where the universe came from is like asking what is north of the North Pole. Perhaps a bouncing universe simply is. It does not need a beginning any more than the number line needs a starting point. These are philosophical questions as much as scientific ones, but they show how thinking about exotic objects, black holes and white holes, and the structure of space-time leads us to profound questions about the nature of reality itself. Let me shift gears and talk about something called the holographic principle. This is another idea from theoretical physics that has implications for what might lurk inside black holes. The holographic principle emerged from studying black holes in the 1970s. Physicists like Jacob Bekenstein and Stephen Hawking discovered something surprising. A black hole has a temperature. It radiates energy, and it has a quantity called entropy that measures how much information it contains. What surprised everyone was how the entropy of a black hole scales. You might expect that the entropy of an object depends on its volume. A bigger object can hold more information, just as a bigger hard drive can store more data. But for black holes, the entropy does not scale with volume. It scales with the surface area of the event horizon. This is bizarre. It is as if all the information about what fell into the black hole is encoded on its surface, not spread throughout its interior. It is as if the interior is somehow redundant, somehow described entirely by what happens at the boundary. This idea was generalized into the holographic principle. The principle suggests that all the information in any region of space can be described by data encoded on the boundary of that region. The interior is a kind of projection, a hologram generated by the information on the surface. If this principle is correct, it has profound implications. It suggests that our three-dimensional universe might be a projection from a two-dimensional surface. It suggests that the fundamental theory of everything might live on the boundary, not in the bulk. This might sound abstract and disconnected from exotic objects like gravastars and white holes. But there is a connection. If black holes are truly described by the holographic principle, then the information that falls into them is not lost. It is preserved on the event horizon. And this might be how the information paradox is resolved. Remember the information paradox. Quantum mechanics says information cannot be destroyed. Black holes seem to eat information and never give it back. Hawking radiation seems to be random, carrying no information about what fell in. But if information is encoded on the event horizon, then Hawking radiation might not be random at all. It might carry subtle correlations, tiny patterns that encode the information about everything that fell into the black hole. The information would escape gradually over the lifetime of the black hole. This is still being debated. The exact mechanism by which information might escape is not fully understood. Different theoretical frameworks give different answers, but the holographic principle provides a framework for thinking about these questions. It suggests that the answers might involve looking at boundaries, at surfaces, at the edges of things. And this brings us back to gravastars. Remember, a gravastar has no singularity at its center. Instead, it has a shell of matter surrounding a core of vacuum energy. The shell is like a surface, a boundary between the extreme interior and the exterior space-time. If the holographic principle applies to gravastars, the information about what went into forming the gravastar might be encoded on that shell. The interior might be a projection of the boundary. The whole object might be understood in terms of what happens at its surface. This is speculative, of course. We do not know if gravastars exist. We do not fully understand how the holographic principle applies to real physical objects. But the connections are intriguing. Different pieces of theoretical physics seem to be pointing in similar directions. Let me tell you about another exotic possibility: baby universes. The idea is that when a black hole forms, the singularity at its center might not be a dead end. Instead, it might be a seed for a new universe. In this picture, the extreme conditions at the center of a black hole create new space-time. A bubble forms. That bubble grows, not into our universe, but into its own separate space. It becomes an entire universe, disconnected from ours. From our perspective, this baby universe would be completely invisible. It would exist beyond our event horizon. We could not send signals to it or receive signals from it. For all practical purposes, it would be another reality, another world, another cosmos. But the laws of physics might be slightly different in that baby universe. The constants of nature, the strength of gravity, the mass of the electron, might have different values. Natural selection might operate among universes. Universes that produce many black holes would create many offspring. Universes that produce few black holes would have few descendants. Over cosmic generations, the multiverse would become dominated by universes that are good at making black holes. This idea is called cosmological natural selection. It was proposed by the physicist Lee Smolin. It is highly speculative. We have no way to test it directly. But it is a fascinating example of how thinking about black holes leads to grand cosmological ideas. If baby universes form inside black holes, then our own universe might be a baby universe too. We might exist inside a black hole that formed in a parent universe. The Big Bang might have been the birth cry of our cosmos, emerging from the seed of a collapsed star in another reality. This is mind-bending stuff. It challenges our ideas about what the universe is and where it came from. It suggests that existence might be far more vast and varied than we can perceive. Let us come back to something more concrete. Let us talk about the density ladder one more time and think about what other rungs might exist. We have ordinary stars, held up by radiation pressure. White dwarfs, held up by electron degeneracy pressure. Neutron stars, held up by neutron degeneracy pressure. And then, supposedly, black holes, where nothing can hold back gravity. But between neutron stars and black holes, there might be other states of matter, other forms of resistance. I mentioned quark stars earlier. In a quark star, the neutrons have broken apart into their constituent quarks, but the quarks themselves might have further structure. There might be preons, hypothetical particles, that make up quarks. If preons exist, there could be preon stars, even denser than quark stars. Going further down the ladder, some theories suggest that space-time itself might have a structure that resists compression. At the Planck scale, as I mentioned with loop quantum gravity, quantum effects in gravity become important. There might be Planck stars, objects held up by quantum gravitational pressure, hovering just at the edge of becoming black holes. Planck stars would be incredibly tiny. Remember, the Planck length is about 10 to the minus 35 meters. That is far smaller than any atom, any proton, any quark. A Planck star would be invisible, undetectable by any current technology. But Planck stars might leave signatures. If they form at the centers of black holes, as loop quantum gravity suggests, they might affect how black holes behave over very long timescales. They might emit unusual particles as they evaporate. They might produce distinctive gravitational waves. The density ladder might have many rungs we have not yet climbed. Each rung represents a new form of matter, a new way for the universe to resist gravity's pull. And each rung might host its own exotic objects, its own strange phenomena, its own surprises. I want to pause here and reflect on how remarkable all of this is. We are primates on a small planet orbiting an ordinary star in the suburbs of a spiral galaxy. Our brains evolved to help us find food and avoid predators on the African savanna. And yet, here we are, contemplating the nature of black holes and white holes, gravastars and wormholes, the topology of space-time, and the origins of the universe. Human curiosity is an amazing thing. It drives us to ask questions that have no immediate practical application. Why is the sky blue? Why do the planets move the way they do? What happens at the center of a black hole? These questions do not help us survive in any direct sense, but they make our lives richer. They connect us to something larger than ourselves. The universe does not owe us answers. It is under no obligation to be comprehensible. And yet, remarkably, it seems to be. The same mathematics that describes the arc of a thrown ball describes the orbits of galaxies. The same physics that explains the behavior of light in a laboratory explains the behavior of light near a black hole. There is a deep unity to nature, a coherence that we can discover and describe. This is not a guaranteed thing. There was no a priori reason to expect the universe to be mathematical. No reason to expect that equations written on paper would match the behavior of real physical systems. And yet they do. Einstein's equations, written a century ago, predicted gravitational waves that we only detected a few years ago. The match between theory and observation is astonishing. This gives me confidence that our speculations about exotic objects are on the right track. Not all of them will turn out to be correct, of course. Some of our ideas are probably wrong. But the overall approach, using mathematics to explore possibilities and then looking for observational evidence, has a proven track record. It has led us to discoveries that would have seemed magical to our ancestors. So when I tell you about gravastars and white holes, I am not telling you fairy tales. I am telling you about possibilities that are grounded in serious physics, possibilities that might be confirmed or ruled out within our lifetimes, possibilities that, if true, would transform our understanding of reality. That is worth staying awake for, even on a night when sleep is calling. Let us talk about the challenges of observing these exotic objects in more detail, because the gap between theory and observation is where the real adventure happens. Consider the Event Horizon Telescope. This is not a single telescope, but a network of radio telescopes spread across the globe. By combining their observations, astronomers can effectively create a telescope the size of Earth. This allows them to resolve details smaller than any single telescope could see. In 2019, the Event Horizon Telescope produced the first direct image of a black hole's shadow. The object was at the center of the galaxy M87, about 55 million light-years away. The image showed a bright ring of glowing gas surrounding a dark central region. That dark region is the shadow of the event horizon. The image was beautiful. It confirmed what general relativity had predicted. It showed that massive compact objects at the centers of galaxies behave the way we expected black holes to behave. But here is the thing. The image also could not rule out alternatives. A gravastar massive enough would cast nearly the same shadow. A boson star, another hypothetical object made of exotic particles, might look similar too. The resolution of the image, while impressive, was not fine enough to distinguish between these possibilities. This is the challenge. Different exotic objects make subtly different predictions, but the differences are often smaller than our current ability to measure. We need better telescopes, more sensitive detectors, more data. The good news is that technology keeps improving. The Event Horizon Telescope is being upgraded. New radio telescopes are being added to the network. Plans are being made to extend the network into space, which would dramatically increase its resolution. Within the next decade or two, we might have images of black hole shadows that are 10 or 100 times sharper than today's images. We might be able to see details near the event horizon that would reveal whether the object is a true black hole or something else. Gravitational wave astronomy is another frontier. Since 2015, we have been detecting gravitational waves from merging compact objects. Most of these mergers involve objects that are consistent with being black holes. But the gravitational wave signals carry information that we have not yet fully decoded. When two black holes spiral together and merge, the resulting gravitational waves have a characteristic shape. There is a chirp as the two objects spiral inward, getting faster and faster. Then there is a burst as they merge. Finally, there is a ring down, as the merged object settles into its final state. The ring-down is particularly interesting. During this phase, the merged black hole is vibrating, shedding excess energy as gravitational waves. The frequencies and decay rates of these vibrations depend on the properties of the final object. For a true black hole, general relativity makes precise predictions about the ring-down. The vibration frequencies, called quasi-normal modes, depend only on the mass and spin of the black hole, nothing else. But for a gravastar or other exotic object, the ring-down might be different. There might be echoes. The gravitational waves might reflect off internal structures and come bouncing back out, producing a delayed signal. Researchers have looked for echoes in the LIGO and Virgo data. Some analyses have claimed tentative evidence for echoes. Others have found nothing. The signals are faint and the noise is significant. It is hard to tell if there is really something there, or if we are just seeing random fluctuations. This is how science often works. Evidence accumulates slowly. Initial hints are ambiguous. It takes time and more data to reach firm conclusions. But the potential reward is enormous. If we found clear evidence for echoes in gravitational wave signals, it would mean that the merging objects were not true black holes. It would mean that something is happening behind the apparent event horizon. It would crack open our understanding of extreme gravity. Another observational avenue involves pulsars. Pulsars are rapidly spinning neutron stars that emit beams of radiation from their magnetic poles. As they spin, these beams sweep across space like lighthouse beacons. If a beam happens to point toward Earth, we see a pulse of radio waves. Pulsars are incredibly precise natural clocks. Some of them keep time better than atomic clocks on Earth. This precision makes them useful for detecting subtle effects in their environment. If a pulsar is orbiting a black hole, the precise timing of its pulses can reveal information about the black hole. The pulses will be delayed when they pass near the black hole, due to the curvature of space-time. They might also show effects from frame dragging if the black hole is spinning. Astronomers have been searching for a pulsar orbiting the supermassive object at the center of our own galaxy, Sagittarius A star. So far, no pulsar has been found in a sufficiently close orbit. But the search continues. If such a pulsar is found, it would be an incredible laboratory for testing general relativity and potentially for distinguishing between black holes and exotic alternatives. Let me also mention neutrino astronomy. Neutrinos are ghostly particles that interact very weakly with matter. Trillions of neutrinos are passing through your body right now without affecting you at all. Because they interact so weakly, neutrinos can escape from environments that light cannot. If matter is falling into a black hole, some of that matter might produce neutrinos before it crosses the event horizon. These neutrinos could escape and travel across the universe to reach our detectors. We have detected high-energy neutrinos from distant sources using detectors like IceCube in Antarctica. Some of these neutrinos might come from the environments around black holes. By studying these neutrinos, we might learn something about what happens just outside the event horizon. For exotic objects like gravastars, the neutrino signatures might be different. If the object has a physical surface instead of an event horizon, matter hitting that surface might produce different particles and radiation than matter crossing an event horizon would. These differences might show up in the neutrinos we detect. This is still a developing field. Our neutrino detectors are not yet sensitive enough to make definitive statements about the nature of distant compact objects. But the technology is improving. Larger detectors are being planned. The era of multi-messenger astronomy, combining observations of light and gravitational waves and neutrinos, is just beginning. Let me step back and talk about something more philosophical. Why does it matter whether black holes are actually black holes or something else? At one level, it matters because we want to understand the universe. We want to know what is out there. We want to fill in the map. That curiosity is reason enough. But there is a deeper level too. The nature of black holes is connected to some of the most fundamental questions in physics. What happens when gravity becomes extreme? How do quantum mechanics and general relativity fit together? Is information truly conserved? What is the nature of space-time at the smallest scales? If black holes are exactly what general relativity predicts, with singularities at their centers and perfect event horizons, then we learn something about the limits of quantum effects. Quantum mechanics might not prevent singularities from forming. The smoothness of space-time might persist even at the smallest scales. But if black holes are actually gravastars or fuzzballs or bouncing objects that eventually become white holes, then quantum effects are more powerful than we thought. They can prevent singularities. They can modify the structure of space-time. They can resolve paradoxes that seem unresolvable in classical physics. This matters not just for understanding black holes, but for understanding everything. If quantum effects can modify extreme gravitational situations, they might have left traces elsewhere too. In the cosmic microwave background, in the large-scale structure of the universe, in the behavior of matter at high energies, the answers to questions about black holes might be the keys that unlock deeper mysteries. They might show us how to build a complete theory of quantum gravity. They might reveal the ultimate structure of reality. I am not exaggerating when I say that these are among the most important questions in all of physics. The nature of space-time, the origin of the universe, the laws that govern everything. These are the questions that exotic objects like gravastars and white holes are connected to. Let me talk about time for a moment. Time is one of the strangest aspects of black holes and their potential alternatives. In our everyday experience, time flows steadily. Seconds tick by. Minutes accumulate. We age. Events happen in sequence, cause followed by effect. But near a black hole, time behaves very differently. The closer you get to the event horizon, the slower time passes relative to someone far away. An astronaut falling into a black hole would feel time passing normally for themselves. But to a distant observer, the astronaut would seem to slow down, moving more and more sluggishly, their clock ticking more and more slowly. This is not just an optical illusion. It is real. Time genuinely passes at different rates in different gravitational fields. Atomic clocks on GPS satellites tick faster than identical clocks on the surface of Earth, because the satellites are farther from Earth's gravitational well. This effect is tiny, but it is measurable and must be corrected for GPS to work accurately. At the event horizon of a black hole, this effect becomes extreme. From a distant perspective, time stops at the horizon. An object crossing the horizon would appear to freeze, becoming dimmer and more redshifted until it fades from view entirely. But from the object's own perspective, time continues normally. The horizon crossing is not a special moment. The astronaut would not notice anything unusual as they pass the event horizon. They would only realize something was wrong later, when they found themselves unable to escape, falling inexorably toward the center. This asymmetry between the internal and external perspectives creates strange situations. Consider two astronauts. One falls into a black hole. One stays outside to watch. The falling astronaut reaches the center, whatever is there, and their story ends, at least from their own perspective. But the watching astronaut never sees this happen. From their perspective, the falling astronaut is still at the horizon, frozen in time, forever falling, but never quite crossing. In a sense, the falling astronaut exists in two states simultaneously. Ended, from their own perspective. Eternally suspended, from the outside perspective. Time is not universal, it is local. Different observers can have genuinely different experiences of the same events. If black holes eventually become white holes through a quantum bounce, this asymmetry takes on new significance. The bounce might happen almost instantly for the falling matter, but from the outside, it takes an extremely long time. Billions of years, trillions of years. The black hole evaporates through Hawking radiation, shrinking slowly, and only when it becomes very small does the bounce finally complete. This means that information falling into a black hole is not lost, but it is inaccessible for a very long time. From a practical standpoint, it might as well be lost. You would have to wait longer than the current age of the universe to get it back. But in principle, the information survives. It is encoded in the structure of the black hole. It waits, patient and unchanging from its own perspective, while eons pass in the outside universe. And then, one day, it comes bursting back out as the white hole erupts. This is a strange kind of immortality. Information cannot be destroyed, but it can be delayed. It can be put on hold, suspended in the frozen time of a black hole, until the universe is unimaginably old. I find this oddly comforting. Even the most extreme events, even falling into a black hole, do not truly destroy information. The universe keeps records. Nothing is forgotten, not completely. Given enough time, everything returns. Let me talk about the arrow of time more broadly. In physics, most fundamental laws are time reversible. If you take the equations of motion and run them backward, they still work. A ball thrown up into the air and falling back down looks the same whether you play the movie forward or backward. But our everyday experience has a clear arrow of time. Eggs break, but do not unbreak. Coffee cools but does not spontaneously heat up. We remember the past but not the future. Why? The answer has to do with entropy, the measure of disorder. The second law of thermodynamics says that entropy tends to increase. Systems evolve from ordered to disordered states. This gives time its direction. The future is the direction in which entropy is higher. Black holes have enormous entropy. In fact, a black hole has the maximum entropy that can fit in a region of space of that size. This is related to the holographic principle I mentioned earlier. The information capacity of a black hole is proportional to its surface area. When matter falls into a black hole, entropy increases. Information becomes hidden behind the event horizon. The universe becomes more disordered, at least from our perspective. But if black holes eventually become white holes, this process might reverse. The hidden entropy might be released. The information might come flooding back out. In a sense, the arrow of time might momentarily flip near a white hole. This is speculative, of course. We do not fully understand the thermodynamics of white holes. They might not even exist. But if they do, they would be fascinating laboratories for studying the arrow of time. The connection between time, information, and gravity is one of the deepest in physics. Black holes sit at the intersection of all three. Understanding black holes might be the key to understanding time itself. Let me return to the human perspective for a moment. Here we are, on our tiny planet, looking up at the stars. The nearest black hole we know of is about 1,500 light-years away. The nearest supermassive black hole is at the center of our own galaxy, about 26,000 light-years away. We will never visit these objects, not in any foreseeable future. The distances are too vast. The energies required for such journeys are too immense. We are confined to our cosmic neighborhood, our solar system, perhaps someday our nearby stars. And yet we can study these objects. We can detect the light they emit. We can feel the gravitational waves they produce. We can build mathematical models that describe their behavior. We can imagine what it would be like to fall into one, to experience the extreme curvature of space-time, to cross an event horizon. This is the remarkable power of science. It extends our reach far beyond our physical grasp. It allows us to explore the universe without leaving our planet. It lets us ask questions and find answers about places we can never touch. And the answers we find reshape our understanding of everything. They change how we think about space and time, matter and energy, cause and effect. They show us that the universe is far stranger and more wonderful than common sense would suggest. Black holes are one of the clearest examples of this strangeness. They are objects that defy our intuition, regions of space where nothing can escape, places where time stops, boundaries beyond which we cannot see, and yet we have found them. We have measured their masses, we have imaged their shadows, we have listened to their gravitational songs. They are real, they exist, they are part of the universe we inhabit. The exotic alternatives to black holes, the gravitar stars and white holes and fuzzballs, are still in the realm of theory. We do not know if they exist, but the fact that we can imagine them, that we can write down equations describing them, that we can make predictions about how they would behave, is itself remarkable. We are mapping the possible. We are charting the waters of what the universe might contain. And with every new observation, with every new data point, we are narrowing down the possibilities. We are converging on the truth. That journey is ongoing. It will continue long after we are gone. Future generations will have better telescopes, more sensitive detectors, deeper theories. They will answer questions we cannot yet answer. They will ask questions we cannot yet imagine. And perhaps they will discover that the universe contains objects we have not yet dreamed of. Objects stranger than gravastars, stranger than white holes, stranger than anything in our current theories. The universe has surprised us before. It will surprise us again. That is something to look forward to, even as we drift towards sleep. The future holds mysteries. The future holds discoveries. The future holds a universe full of wonders. Let me weave together the threads we have been exploring. We started with a simple observation. Black holes are strange, but they might not be the strangest objects in space. We then journeyed through a landscape of exotic possibilities. Gravastars with their cores of dark energy. White holes erupting matter into the void. Spinning black holes with ring singularities that might be gateways to other regions of spacetime. Quark stars and strange stars made of matter in forms we have never seen on Earth. Fuzzballs from string theory, bouncing black holes from loop quantum gravity. Each of these objects represents a different answer to the question, what happens when gravity becomes extreme? General relativity says matter collapses all the way to a singularity, a point of infinite density where the equations break down. But maybe that is not the whole story. Maybe quantum effects intervene. Maybe new forms of matter appear. Maybe spacetime itself has structure that resists compression. We do not know yet which of these possibilities is correct. We do not know if any of them is correct. But the very existence of these possibilities tells us something important. It tells us that our understanding of extreme gravity is incomplete. It tells us that black holes, for all their fame, might be just the surface of something deeper. Now, let us think about the life cycle of the universe from this perspective. Stars are born from clouds of gas and dust. Gravity pulls the gas together. The center gets dense and hot. Nuclear fusion ignites. A star shines. Stars live for millions or billions of years, depending on their mass. They burn through their nuclear fuel. They produce heavy elements like carbon and oxygen and iron. They enrich the cosmos with the building blocks of planets and life. Stars die. Small stars fade gently into white dwarfs, slowly cooling over billions of years. Massive stars explode as supernovae, scattering their enriched gas across space. The cores that remain behind become neutron stars or black holes. Black holes grow. They absorb matter that falls too close. They merge with other black holes. The supermassive black holes at the centers of galaxies have grown to contain millions or billions of times the mass of our Sun. But black holes do not live forever. They evaporate through Hawking radiation, very slowly, over timescales that dwarf the current age of the universe. They shrink. They get smaller and smaller, until eventually they reach a critical point. And then what? In the standard picture, black holes evaporate completely, leaving behind nothing. All the information they contained is either released in the Hawking radiation or lost forever. But in the picture offered by loop quantum gravity, something different happens. When a black hole shrinks to the Planck scale, it bounces. It becomes a white hole. All the matter and information that fell in over billions of years comes erupting back out. If this picture is correct, then black holes are not the end of the road. They are waypoints. They are temporary storage facilities for matter and information. What goes in eventually comes back out. This has profound implications for the far future of the universe. In the very distant future, all the stars will have burned out. All the galaxies will have dissipated. The universe will be dark and cold, populated only by the remnants of stars and by black holes slowly evaporating. But if black holes bounce, then even that dark era is not the final chapter. Billions of years from now, the remaining black holes will complete their bounces. White holes will erupt, briefly illuminating the darkness. Matter and energy will return to the universe. What happens then is unclear. Maybe the returned matter and energy just dissipate into the void, fading away forever. Maybe they clump together again, forming new structures, maybe even new stars in some unimaginably distant future. Maybe the universe goes through cycles, contracting and bouncing, expanding and contracting, forever. This is the cosmic perspective. From this vantage point, our current era is just a moment, a brief flicker of activity between two infinities. The universe is young, cosmically speaking. Most of what will happen has not happened yet. And the exotic objects we have been discussing, the gravastars and white holes and the rest, might play crucial roles in that future. They might be the mechanisms by which information is preserved. They might be the seeds of new eras, new structures, new possibilities. Let me spend some time now on the emotional texture of these ideas, because science is not just a collection of facts. It is a way of relating to the universe. It shapes how we feel about our place in the cosmos. When I think about black holes, I feel a sense of awe. These are objects of incredible power. They warp space-time so severely that nothing can escape their grip. They contain regions where the normal rules break down. They are the most extreme objects we know of. But when I think about the alternatives to black holes, I feel something different. I feel hope. Because the alternatives suggest that the universe might be kinder than it appears. Singularities might not exist. Information might not be lost. Time might not be the one-way street we assume it is. Gravastars, if they exist, are objects without singularities. Inside a gravastar, you could float freely. There would be no crushing gravity, no point of infinite density. The universe would hold you gently. White holes, if they exist, are objects that return what was taken. They release matter and energy into the cosmos. They balance the cosmic books. They suggest that nothing is truly lost, that everything eventually comes back. These are not just scientific ideas. They are, in a way, stories about the nature of reality. Stories that carry emotional weight. Stories that shape how we feel about the universe we inhabit. I am not saying we should believe in gravastars or white holes because they are comforting. Science does not work that way. We should follow the evidence wherever it leads, even if it leads somewhere uncomfortable. But the fact that the mathematics allows for these kind of possibilities is itself noteworthy. The universe did not have to be this way. It could have been a place where singularities are inevitable, where information is always destroyed, where the arrow of time points only toward destruction. But it might not be, and that is worth contemplating. As you lie there in the darkness, drifting toward sleep, consider that the cosmos might be more generous than it first appears. Consider that even the most extreme events might not be final. Consider that the story is still being written. Let me tell you about the concept of cosmic patience. There is a quantity in physics called the information recovery time. This is the timescale over which information about what fell into a black hole can be retrieved from the Hawking radiation. Calculations suggest that for a large black hole, this time is incredibly long, much longer than the current age of the universe, maybe as long as the black hole's entire evaporation time. What this means is that even if information is preserved, even if it eventually comes back out, the process is extraordinarily slow. From a practical perspective, information that falls into a black hole is gone. You will not see it again in your lifetime. You will not see it again in the lifetime of human civilization. You might not see it again until stars have stopped forming and the universe has grown unimaginably old. This is a kind of cosmic patience that humans cannot easily relate to. Our lives are short. Our attention spans are shorter. We want answers now, not in 1 trillion years. But the universe operates on its own timescales. It does not care about human impatience. It unfolds according to its own rhythms, its own laws, its own vast temporal expanses. And from the universe's perspective, 1 trillion years is not so long. It is just another chapter, another beat in the cosmic heartbeat. The universe has time to spare. This perspective can be humbling. It can make our concerns seem small, but it can also be liberating. It reminds us that we are part of something vast and ancient and enduring. Our individual lives are brief, but the story of which we are part continues. Let me also say something about the scientific process itself. We have been talking about exotic objects that might or might not exist. This uncertainty might seem frustrating. Why cannot scientists just tell us what is real? But this uncertainty is actually the strength of science, not its weakness. Science is honest about what it does not know. It does not claim certainty where none exists. It offers possibilities, predictions, hypotheses, and then looks for evidence. When a scientist says that gravastars might exist, they are not being wishy-washy. They are being precise. They are acknowledging that the mathematics permits gravastars, but that we have not yet found observational evidence for them. They are inviting further investigation, further observation, further testing. This is how knowledge advances. We propose ideas, we test them. We keep the ones that survive the tests, and discard the ones that fail. Over time, our understanding improves. The map gets more accurate. The exotic objects we have been discussing are currently in the proposal stage. They are ideas that need testing. Some of them might turn out to be real. Others might turn out to be impossible. We will find out by looking, by observing, by measuring. And that is exciting. It means there is still discovery to be done. It means the universe has not yet revealed all its secrets. It means the future holds surprises. Think about the generations of scientists who will come after us. They will have tools we cannot imagine. Telescopes that make ours look primitive. Detectors of incredible sensitivity. Theories that go beyond anything we have conceived. Those future scientists will answer questions we are struggling with today. They will know whether gravastars exist. They will know whether black holes bounce. They will know what happens at the center of a black hole, whether it is a singularity or something else. And they will have new questions of their own, questions we cannot even formulate because we do not yet have the concepts. The frontier of knowledge will have moved, but there will still be a frontier. There always is. This is the great human adventure. Not any single discovery, but the ongoing process of exploration, the endless pushing into the unknown, the persistent asking of questions. We are part of that adventure. Everyone who wonders about the stars, everyone who asks why the universe is the way it is, everyone who refuses to accept that we know everything there is to know. Let me bring our journey to a gentle close. We have traveled far tonight, from the familiar surface of our sun to the extreme densities of white dwarfs and neutron stars, from the event horizons of black holes to the hypothetical surfaces of gravastars, from the one-way boundaries of black holes to the one-way exits of white holes, from the ring singularities of spinning black holes to the quantum foam of loop quantum gravity. We have seen that the universe is stranger than it first appears, that the objects we thought we understood might be more mysterious than we realized, that the math allows for possibilities we have not yet observed. And we have seen that this strangeness is not something to fear. It is something to celebrate. It means the universe is rich. It means there is always more to learn. It means the story is not over. Black holes are not the strangest objects in space. They are just the most famous. Behind them, in the shadows, other objects might be lurking. Gravastars holding bubbles of dark energy. White holes waiting to erupt. Quark stars pulsing with exotic matter. Wormholes threading through the fabric of reality. We do not know for certain that any of these objects exist, but we know they might. And that might is a kind of promise. A promise that the universe still has secrets. A promise that discovery still awaits. So as you drift towards sleep, carry these ideas with you. Let them float through your dreams. The cosmos is vast and strange and wonderful. It holds wonders we have seen and wonders we have not. It invites us to explore, to question, to wonder. The mathematics has shown us what might be possible. Our telescopes and detectors are searching for what is real. Somewhere out there, the answers are waiting. And someday, perhaps soon, we will find them. Until then, we wonder, we imagine, we dream. The universe is patient. It has been here for nearly 14 billion years. It will be here for trillions more. It can wait for us to catch up. It can wait for us to develop the tools we need. It can wait for us to ask the right questions. And while it waits, it keeps spinning. Galaxies rotate, stars burn, black holes grow and evaporate. The cosmic dance continues, indifferent to our attention, but available for our contemplation. You are part of this dance. Every atom in your body was forged in a star. The oxygen you breathe, the carbon in your cells, the iron in your blood, All of it came from stellar furnaces that burned billions of years ago. You are made of star stuff. You are the universe contemplating itself. And when you look up at the night sky, when you wonder about black holes and gravastars and white holes, you are continuing a tradition as old as humanity. The tradition of looking up and asking why. The tradition of refusing to accept ignorance. The tradition of reaching for the stars. That tradition will continue long after we are gone. Future generations will carry it forward. They will build on what we have learned. They will go further than we can imagine. But for now, in this moment, let the wonder wash over you. Let the strangeness of the cosmos soothe you. Let the vastness put your worries in perspective. The universe is beautiful. It is mysterious. It is home. Good night. Sleep well. And dream of the stars. The darkness around you is not empty. It is full of light traveling from distant galaxies, full of gravitational waves rippling from ancient collisions, full of possibilities we have not yet imagined. Rest now. The universe will be here when you wake, ready for another day of wonder, another day of questions, another day of the great adventure. Sweet dreams. Let me share a few more thoughts before we truly conclude. I have been thinking about what it means to exist in a universe where these exotic objects might be real. It changes something fundamental about how we see reality. When you grow up, you learn certain things about the world. You learn that objects fall when you drop them. You learn that time moves forward. You learn that what goes up must come down. These lessons become part of your intuition. They shape how you expect the world to behave. But then you start learning physics, and you discover that your intuitions, while useful for everyday life, are only approximations. They work on the scales of human experience, but they break down at the very large and the very small. They fail in extreme conditions. This is humbling, but it is also exhilarating. It means there is more to reality than what meets the eye. It means the universe is deeper than our first impressions suggest. Black holes are perhaps the most dramatic example of this. Nothing in our everyday experience prepares us for objects where space and time become so distorted. Nothing in our intuition suggests that such things could exist, and yet they do. The mathematics predicted them. The observations confirmed them. The exotic alternatives to black holes push this even further. Gravastars suggest that emptiness can have pressure. White holes suggest that cosmic processes can run in reverse. Wormholes suggest that distant points in space might be secretly connected. Each of these ideas challenges our intuitions. Each of them asks us to expand our sense of what is possible. Each of them invites us into a universe stranger and richer than the one we thought we knew. I think this is one of the great gifts of science. It does not just tell us facts. It transforms how we see. It opens doors we did not know existed. It reveals landscapes beyond our imagination. And the journey is not over. The exotic objects we have discussed tonight are still being explored. New theories are being developed. New observations are being made. The frontier keeps moving. There is something beautiful about being alive at this moment in history. We know enough to ask profound questions about the nature of space-time and gravity, but we do not know so much that all the mysteries are solved. We are at that sweet spot where wonder and knowledge intersect. Future generations might look back at our era and smile. They might think our theories were naive. They might have answers to questions we struggle with, but they will also have their own frontiers, their own mysteries, their own edges of the unknown. The human adventure of understanding the cosmos will continue as long as there are humans to wonder. Let me say something about the nature of darkness. Not the darkness of space, but the darkness of night. the darkness that surrounds you now as you listen. Darkness can feel empty. It can feel like an absence. But really, darkness is just a different kind of presence. It is the presence of all the light we cannot see, infrared radiation from warm objects, radio waves from distant galaxies, gravitational waves from colliding black holes. The darkness is full of information, full of energy, full of the universe expressing itself in frequencies beyond our eyes. When ancient people looked up at the night sky, they saw stars scattered across a dark background. They did not know what those stars were. They did not know how far away they were. They did not know that each star was a sun, that many of those suns had planets, that the darkness between the stars stretched for light years. We know more now, but we still do not know everything. The darkness still holds secrets, and that is okay. That is more than okay. That is wonderful. The universe does not owe us its secrets all at once. It reveals them slowly to those who look carefully, to those who ask the right questions, to those who are patient. Think about what we have learned in just the last century. General relativity, quantum mechanics, the expansion of the universe, dark matter, dark energy, gravitational waves, the cosmic microwave background. Each of these discoveries transformed our understanding of reality. Each of them was waiting in the darkness, ready to be found. What discoveries are waiting for us now? What truths are hidden in the data we are collecting? What objects lurk in the shadows of space-time, predicted by our equations, but not yet confirmed by our instruments? We do not know. That is the point. That is the adventure. Let me circle back to where we began. I told you that black holes are not the strangest objects in space. I told you that the universe might contain gravastars and white holes and other exotic things. I told you that the mathematics predicts more than we have found. But let me add something to that. Even if none of these exotic objects exist, even if black holes turn out to be exactly what general relativity predicts, the universe is still strange. It is still full of wonders. Consider just the ordinary facts. Stars are balls of burning gas, held together by gravity, powered by nuclear fusion. Neutron stars are city-sized balls of neutrons, spinning hundreds of times per second, with magnetic fields 1 trillion times stronger than Earth's. Black holes are regions where space-time curves so severely that nothing can escape. These are ordinary facts, in the sense that they are well established. They are not speculative. They are not exotic alternatives. They are what we know, and yet they are extraordinary. They are staggering. They are the kind of things that should make us pause in wonder every time we think about them. The universe does not need exotic objects to be amazing. It is amazing already. The exotic objects, if they exist, are just additional layers of amazement, extra wonders piled on top of wonders. This is the proper frame of mind for contemplating the cosmos, not jaded familiarity, but fresh astonishment. The universe is incredible. Let yourself feel that. As you drift towards sleep, let the wonder fill you. Let the vastness expand your sense of possibility. Let the strangeness loosen your assumptions about what is real. Tomorrow you will wake to the ordinary world, the world of gravity and sunlight, of breakfast and work, of friends and family. That world is wonderful too, in its own way. But tonight, let yourself dream of the extraordinary. Dream of stars collapsing into objects denser than anything on Earth. Dream of space-time warping into impossible shapes. Dream of information preserved across billions of years. Dream of matter erupting from white holes into the void. These are not just fantasies. They are possibilities. They are what the mathematics allows. they are what the universe might contain. And even if they turn out not to exist, the dreaming itself is valuable. It stretches our minds. It expands our sense of what is possible. It prepares us for whatever the universe actually turns out to be. The cosmos is vast. Our corner of it is small. But our minds can reach across the light years. Our imagination can visit places our bodies never will. That is the power of thought. That is the gift of curiosity. That is the magic of wondering. So wonder. Wonder about black holes and their alternatives. Wonder about the far future of the universe. Wonder about the nature of time and space. Wonder about everything. The universe rewards those who wonder. It opens itself to those who ask. It shares its secrets with those who seek. You are a seeker. By listening to this, by thinking about these ideas, by letting your mind drift among the stars, you have joined the great community of seekers, the community that stretches back to the first human who looked up at the sky and asked why. Welcome to that community. You belong here. Now rest. Let your mind relax. Let the ideas we have explored settle into your subconscious. Let them become part of how you see the world. Tomorrow the sun will rise. The ordinary day will begin. But somewhere inside you, the wonder will remain. The sense that the universe is stranger and more beautiful than it appears. The knowledge that there are mysteries still to be solved. Carry that wonder with you. Let it color your days. Let it remind you that the world is not mundane. That even the most familiar things, gravity and light and time, are extraordinary when you look closely. The cosmos is speaking to us in the light of distant stars, in the ripples of gravitational waves, in the equations we write on paper. It is telling us about itself. It is sharing its secrets. All we have to do is listen. Good night. The universe holds you. The stars are shining. Somewhere out there, the strangest objects in space are waiting to be found. Sleep well, dream deep, and wake ready to wonder again. There is one more thing I want to share with you before we part. Throughout this journey, we have talked about objects and theories and observations. We have talked about physics and mathematics and the scientific method. But underneath all of that, there is something more basic, something more human. There is awe. Awe is the feeling you get when you encounter something vast and mysterious, something that makes you feel small but not insignificant, something that reminds you that the world is bigger than your everyday concerns. The cosmos is the ultimate source of awe. It is vast beyond comprehension. It is old beyond imagining. It contains wonders that surpass anything humans have created. When you feel awe, something happens in your mind. Your sense of self becomes less rigid. Your boundaries soften. You feel connected to something larger. Studies have shown that awe has genuine psychological benefits. It reduces stress. It increases generosity. It makes people more curious and open-minded. It is good for us in ways that science is only beginning to understand. So the time you have spent tonight listening to ideas about black holes and gravastars and white holes has not just been about learning facts. It has been about cultivating awe, about opening yourself to the vastness of existence, about remembering that there is more to life than the immediate and the familiar. This is valuable. This is important. In a world full of distractions and worries, taking time to contemplate the cosmos is a kind of medicine. It heals something in us that we might not even know is wounded. I hope you feel that healing tonight. I hope the awe has touched you. I hope you go to sleep with a sense of wonder that stays with you. The universe is incredible. Never forget that. Never let the busyness of life obscure the fundamental strangeness and beauty of existence. You are a collection of atoms that somehow became conscious. You are the universe looking at itself. You are a miracle, whether or not you believe in miracles, and you live in a cosmos that might contain gravastars and white holes. A cosmos where space-time can bend and twist. A cosmos where the strangest mathematics might describe actual reality. What a privilege. What an adventure. What a gift. Hold on to that feeling. Let it be your companion. Let it guide you through the challenges of ordinary life. The stars are always there, even when clouds obscure them. The cosmos is always vast, even when you forget to look up. The wonder is always available, even when you get lost in routine. Tonight you remembered. Tonight you looked up. Tonight you let yourself wonder. Thank you for that. Thank you for joining me on this journey. Thank you for being curious, for being open, for being willing to dream. The universe is lucky to have beings like you. Beings who wonder, beings who question, beings who refuse to take existence for granted. May your dreams be full of stars. May your sleep be restful and deep. May you wake refreshed and ready for another day in this strange and wonderful cosmos. The night is gentle. The darkness is kind. The universe is vast and old and beautiful. Rest now. You have earned it. And know that somewhere right now, light is streaming toward Earth from objects billions of light years away. Gravitational waves are rippling through space-time from collisions that happened eons ago. Black holes are slowly evaporating, perhaps bouncing into white holes at their cores. The cosmic drama continues, whether or not we are watching, but we are watching. We are part of it. We are the universe becoming aware of itself. What a strange and wonderful thing to be. Good night, friend. The stars are with you. The cosmos embraces you. Sleep well and dream of wonders yet to come. Tomorrow is another day for discovery, another day for questions, another day for the great human adventure of understanding. But that is tomorrow. Tonight is for rest. Tonight is for peace. Tonight is for letting go and drifting into the gentle darkness. The universe will hold you. It always has. It always will. Sleep now. The stars are singing their ancient songs. The gravity waves are humming their deep vibrations. The cosmos is playing its endless symphony, and you are part of the music. Good night. The journey we have taken tonight is just one thread in the vast tapestry of cosmic understanding. There are so many more threads to explore, so many more questions to ask, so many more wonders to discover. Perhaps one day, future generations will listen to stories about objects even stranger than the ones we discussed. Objects we cannot yet imagine. Phenomena that would astonish even the most seasoned physicist of our era. The universe keeps surprising us. It keeps revealing new layers of complexity and beauty. Every answer leads to new questions. Every discovery opens new horizons. That is the nature of the cosmic adventure. It has no end. It goes on forever, as long as there are curious minds to carry it forward. You are one of those curious minds. By wondering about the universe, you become part of its story. By asking questions, you push the frontier of knowledge, even if just a little bit. That matters. That counts. That is meaningful. So sleep now, knowing that your wonder is worthwhile. Your curiosity is a gift. Your dreams of the cosmos are part of the great human project of understanding. The stars are waiting. The mysteries are calling. And tomorrow, the adventure continues. Sweet dreams.